Good morning. Let's talk about area between curves. I know this might feel a little anticlimactic since we just finished up our various techniques of integration, especially trig substitution, which is way out there. You've already seen kind of this concept, and you saw it with, we were talking about Riemann sums too. And this might feel a little underwhelming, but it's important to get the concept. And we're going to go through a few examples of area between curves. So if you haven't guessed yet, the general concept that we're going to go for here is you have your xy coordinates, planes, axes, and you have some curve like this, you have another curve like that, and it says find the area between it. So the general concept that we're going to do a few times is find the area of one through integration, and then we subtract the area of the other, and that leaves us with the area in the middle. You might think, well, this is pretty straightforward. It is. But what makes things start to get complicated is this is leading up to 3D shapes. So you might have this shape and then you revolve it around the y-axis, or you revolve it around the x-axis, and then you're using that area in that 2D to find a 3D shape. And then that's pretty much what we'll do for finding volumes and volumes using areas. So I know that's a pretty succinct intro, but we're just going to jump straight into a few problems. This will be a little bit shorter than most of the ones we do, mostly because I run on forever, and I love to hear myself talk, but there will be slightly less of me talking this time probably. So start with a simple problem. Yeah, simple if you know how to do it. Most problems in life are simple if you know how to do it. Such as life. Okay, so the idea here is we have two curves, and we're going to find the area between the curves. So intuitively, you look at this problem, you're like, all right, I see where this is going. We're going to have a y-axis, we're going to have an x-axis, and we're going to have y equals x. It looks kind of like this. That is a surprisingly straight line. Good for me. And then we're going to have probably something that looks like that, which is x squared. And x squared will also go up this way as well, but we're looking for the area between the curves. So some of the key points we're going to want to know is what the curves generally look like, which curve is above the other curve. In this case, the y equals x is above from 0 to 1, but y equals x squared is above for greater. And we'll probably want to find out the points of intersection first. So to do that, we set the equations equal to each other. So we say x equals x squared, and we can solve this for x equals, divide both sides by x, so we have 1 equals x. We also have x equals 0. Probably should have done that same. There we go. That's more consistent. So then we know that 0 and 1 is where the curves intersect. And on this interval, we know that y equals x is going to be above y equals x squared. So to find the area between them, we'll find the area under y equals x, and we'll subtract off the area of y equals x squared. So before, when we talked about this concept with Riemann sums, we just did one minus the other. But now we're going to do, we counted boxes. This time, we're going to do something like 0 to 1 dx minus 0 to 1 of x squared dx. Now, since these both go to the same limits of integration, 0 to 1 of x, then we can combine them together. So I'm going to move the negative sign to the negative to the inside. And you can do that because you can move scalars in and out. And that negative sign is really just a -1 scalar. Scalar meaning just a number, i.e. not a vector. So we'll have 0 to 1, x minus x squared dx. Use the power rule to integrate. We have x squared over 2 minus x cubed over 3. We add 1 to the exponent and then move the exponent to the bottom from 0 to 1. And that would equal, and then so what we do is we then take the 1, plug it in, minus the 0, plug it in. So we have 1/2, because 1 squared is 1. Then 1 cubed will be 1 minus. Then we'll subtract off 0 for both of these. So it'll be 0 squared over 2 minus 0 cubed over 3. This will be 0. And so we're left with an area under the curve of 1/2 minus 1/3. Now to backtrack to show what happened here is when we combined these two integrals, what we had was we could separate this out, and this could be 1/2. We could do this, we could have left it as two separate integrals and solved each of them by themselves. So the first term in both of these comes from the first integral, which is y equals x, and the second term in both of these comes from the second curve of y equals x squared. So if we had done them both individually, we would have had x squared over 2 from 0 to 1 minus, what is it, x cubed over 3 from 0 to 1. And this would have given us 1/2 minus 0, where we plug in 1 and 0, minus 1/3 minus 0, where we have plug in 1, plug in 0. We'll distribute things out. Yeah, we'll distribute the negative sign. And then when we rearrange things, we can see that, I don't know, something with a little bit more contrast. 1/2 goes there, the -1/3 goes there, the -0 goes over there. Actually, that -0 probably would go there. And that, there we go. That 0 would go there because the negative, positive. So combine them or not combining gives us the same. Well, I guess I should probably finish the problem up just because it's probably bothering people sitting there. So we go with a common denominator. Denominator is the thing on the bottom. Minus 2 over 6 equals 1/6. Huzzah! Win. Yes. Okay. Feel comfortable? Not too overwhelming. And again, visualizing it, we found the area under y equals x from 0 to 1, and we subtracted off the area of y equals x squared, leaving this area in the middle. Okay. Ooh, that was excessive. And I'll lock that into place. There we go. Highlight everything. I'll leave the y equals x squared there. Okay. Bring the next guy up. So, okay, similar concept. So, start by drawing an axis, or axes. Down and over, and arrow, and y, and x. Okay. So we got 1 over x. So let's see, when we plug in 0, we're going to get infinity. So it probably looks something kind of like this. And y equals x is going to look something like this. And x equals 4 is going to look something like this. So this will be 4. When we find 1 over x equals x, then we get x squared equals 1. So x equals plus or minus 1? Oh yeah, I guess it probably because you get the down there too. Okay, we're going to go with plus 1 though. So this will be 1. And then this point here will be 4, 4. So I'm going to Wolfram this just to be sure. I'm pretty much 100% sure that I'm probably mostly correct, but can always be a little bit more sure. So we have, let's see, y equals 1 over x, y equals x, and x equals 4. Bum 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 bum. Bum bum bum. Ooh, alternate form. Yep, that kind of looks like what we got. Okay, I'm good with this. So moving back, we want to find this area right here. And so to do that, we are going to grab my pen, y equals x, y equals 1 over x, and we're going to integrate from 1, this point here, to 4, y equals x minus 1 over x dx. And then we stop at 4 because this is where our line ends. So that is the enclosed area. So we'll do x squared over 2 minus, and the integral of 1 over x is natural log of x. You can rewrite it as x equals -1. Then when you try to do the power rule, get x to 0, which is possible. But then you want to divide by 0, which is totally not possible. Not kosher in any way. Universe blows up, does not exist. So that's kind of a mental cue that, oh, you messed up terribly. And it should be natural log of x, not x to the 0. Okay, focus. One of the things you might be wondering too is why we don't do the plus c. The plus c would be on both sides here, so we do plus c here and plus c here. And then when we subtracted one from the other, the c would cancel out. So, in case you were curious, slight tangent. So this one will be 4 squared over 2 minus natural log of 4. Those 4s don't seem to be... I'm not very good at drawing 4s. Minus this would be 1/2 minus natural log of 1. Okay. Okay. Is that where they equal each other? Y equals x. Yeah, I'm good with that. And natural log of 1 is 0. I'm never quite sure about that. So a lot of times in my calculator, I will do it, because it only takes a second. Do natural log of 0, it says a natural log of 1, and it should say 0. Natural log of 1 is 0. And some natural log of 0 does not exist. But you can try it, and it says, bam, negative infinity. I draw natural. Y equals 1 over x. Yep. Okay, I'm good at this. And then back to the board. So simplifying things slightly. So we have 4 squared, which is 16, over 2, which is 8. This will be 0. And then we'll have minus 1/2. This will be 7.5 minus natural log of 4, which I'm pretty sure you can rewrite as natural log of 2 squared, which equals 2 natural log of 2. But I'm not that worried about that. Okay, so I'm just going to stick with 7.5 minus natural log of 4. And that would be the area between the curves. Okay? Do one more of a similar vein in nature. Should have locked it in place. There we go. 1 more like this. So this one, we got a couple quadratics. And so we're going to have one going up like this, and then one going down, maybe like this, and there's some other numbers involved, and we want to find these 2 points. So I'm going to assume that the big one is on top, the negative is on top, and then the positive is on bottom. I'm going to graph these, but I just want to get a mental picture before I graph them. And you can graph them on your calculator as well. But sometimes when you graph things on your calculator, you don't get quite what you expect, and so it's hard to understand what the picture is showing you if you don't have the right window size. So setting the equations equal to each other to find their intercept points, we'll have 3x squared plus 16x plus 8 equals negative x squared plus 2x plus 2. And then moving everything over to one side, we have 4x squared plus 14x plus 6 equals 0. Maybe we can factor this. So I'll say maybe 4x times, then we'll probably do a 2 and a 3. 2 times 3, and then we'll have a 1 here. Let's see if this gives us... So what I did was I made sure that the first and the last terms work, because 2 times 3 is 6, and 4 times 1 is 4. But it could also be 2 times 2 or 1 and 4, and I'm just going to see if I get 14x. So let's see here, 4x, that's 4x squared, I know that. Okay, 4x, so it's 12x, and then we got 2x, yep, which equals 14x. So this is true. This is a correct factoring. And then solving each of these for 0, so we know that either this would equal 0 or this would equal 0. So 4x plus 2 equals 0, x equals 2 over 4 negative, which equals negative 1/2, okay? Or x equals, let's see here, x plus 3 equals 0, x equals negative 3. So I'm just going to grab this axis, do one of those. Haha, kind of sort of almost works, where we have negative 1/2 here and negative 3 over here. Okay, and we're of course going to go to Wolfram because I am not that confident. Hope. And Wolfram. Oh, Wolfram, my dearest friend. I love Wolfram. Computers are wonderful. Plus 8 and negative x squared plus 2x plus 2. And we got, hey, it is on the negative side. Below 0 though. Didn't see that. Maybe I should have. There's a lot of things I don't see in life. Let's see if I got the right 0 intercepts though. They tell me? Ooh, that's a much better way of writing it. That looks like about negative 1/2 and negative 3. So I'm going to say, yeah, I'm going to call that a win. A win for the home team. Okay. And then the one going down is, so what we're going to do is we're going to put this all over to one side, which we already did. Okay, so back up slightly. So we'll take the integral of negative x squared plus 2x plus 2 dx minus integral 3x squared plus 16x plus 8. So going back to this picture was kind of correct, except that the axis is more up there. And the negative x squared is the one on top. So we want to, do we want to? No. I think we want to find, because we just want to find the area. It doesn't really matter which order we do it, because we're just finding the amount of area in between. So when we find the area underneath, when you take the integral, it's going to give you the area to the axis. So we'll take the area of the 3x squared and subtract off the area from the negative x squared, leaving us the stuff in the middle. So I'm actually going to reverse these two, which we already, let's see here. So I'll do a plus here, negative there, and then we'll set this equal to, so combining these, we will have, or subtracting them, yep. So we should have, we'll do this area, which is 3x squared plus 16x plus 8 minus negative x squared plus 2x plus 2. Okay. And then we get, so the double negatives cancel, we get 4x squared plus 14x plus 6, because we distribute the negative sign. Integral dx. And that's the same as what we did here for our finding the roots. Okay? And so solving this, oh, and we have our limits of integration, -3 to -1/2. So we have 4x cubed over 3 plus 14x squared over 2 plus 6x. Yep. Because it's just the power rule a few times. -3, -1/2. Now, normally I would go through this and do all the math, but I have confidence that you understand that concept by now. So we plug in -1/2 for each of the x's, and you will subtract off the quantity, -3 plugged in for all the x's. And then we get a value. I'm just concerned for the area between the curves here. So if it turns out to be negative, I just take the positive, the absolute value of it. Okay, and that's the general idea behind area between the curves. We'll do one more problem. Kind of probably find like an AP test style type thing. There we go. I probably don't have to bring it up to my square, which is fairly arbitrary, but you know, life is arbitrary, and it works out well. Well, sometimes life works out well, but life is arbitrary, so why should I fight it? That's probably not true. You should probably try and make as much sense as you can. Okay, so we have a graph. The graph of the continuous function g, okay? The derivative of f of x. Okay, so this is saying that g of x equals f prime of x. So I'm just going to replace this with f prime of x. So this graph is the derivative of f. You see this a lot on the AP exam, where it feels like there's tricky words and phrases just to make life more confusing without actually making it conceptually more difficult. F prime of x. Okay. As shown above, the function g is piecewise linear for -5 to 3. Okay, so that means that they just have straight lines. And g of x equals a quadratic for this point. Okay, and you can see here too is the +4, so it's like a quadratic that's starting at x equals 4, at 4, 0, 4, 3 to 6. Okay. Okay. if f of 1 equals 3, what is the value of f of negative 5? Okay, so if we take the integral of g of x dx, because this feels like there's going to be some integration involved, would equal integral of f prime of x dx, which should equal, and we'll do this from, they give us negative 5 and 1 as the values for the inputs. Negative 5 and 1. And they told us earlier that f prime of x is the same as g of x. So this would be f of 1 minus f of negative 5. So it's the top minus the bottom. And normally you're used to seeing f capital, whereas the antiderivative, but here they specifically gave us a graph of f prime of x. So we get normal normal f. And let's see here. So we can find this because it's up to this point here. And we know it's all piecewise similar, so that's just triangles. We're going to use triangles and squares and find the area under the curve, and they gave us that f of 1 equals 3. So this is 3. So they want us to find f of 5, f of negative 5. So f of negative 5, this is just rearranging, is f of 1 minus integral g of x dx from negative 5 to 1. So I'm going to find this value right now. So it's just the area under the curve. So here we have 1, 2, 3 by 3, which gives us 9. This is 3 by 1, so this will be 3 halves, which is, so it'll be 3 times 1 divided by 2, because it's a triangle. And then this part will be 0, and this will be 1 half, because it'll be 1 times 2. No, that's 1. Outrageous. 1 times 2 divided by 2, 1 half of 1 times 2, because it's a triangle. The formula for the area of a triangle, if you hadn't figured it out, is 1 half base times height. So these two will be negative, and that one will be positive. So we will have, writing this out, see if I can make this big enough real estate. Okay, equals 3 minus, this will be quantity, negative 9 minus, what was it? It was 3 times 1 over 2 plus 1 times 2 over 2. And then 9 was just 3 times 3. So those cancel. This is really going to test my math skills here. So we have 9. So negative 10.5 plus 1 equals negative 9.5. And then 3 minus a negative gives us a positive, which equals 12.5. Huzzah! Yes! Bam! Winner. Okay. So answer to number A is the value of f to negative 5, or f of negative 5, is 12.5. Okay, so now we need to evaluate the integral of 1 to 6. So before we did this, and we just did counting of squares. This time the squares get more difficult to count because we have an actual equation here, which is not linear. And once we get things that are non-linear, boxes become significantly, exponentially more difficult to count. So, but we can still count boxes between 1 and 3. So, green, 1 to 6. So we'll do, start here, area under the curve, 4. Okay, and now we'll do integral from 3 to 6. And what we did here was we took integral of 1 to 6, g of x dx equals, let's see, 1 to 3 g of x dx plus 3 to 6 g of x dx. We just broke them apart, and we knew from our box counting up there that this part equaled 4. I'm going to erase a few things just to declutter my, hopefully my work area and my thought process. A clear desk is a clear mind, maybe? I don't know. One of those ancient Chinese sayings. I don't know if they had desks in ancient China. Probably. Desks have been around for a while. Okay. Focus. Focus. So we have 3 to 6 of 2x minus 4 squared dx. So we'll move the 2 to the outside. Integral, we'll say that u, I'm going to do a U-Substitution here. Most of you are probably smart to see where this is going with it. I am not. So we have du equals dx. This is then u squared du, which is 2u cubed over 3. You can see how I purposely left off the limits of integration there. That way, that's because I'm going to go back to x, and I don't need to convert them over. Though if I could have, I would plug 3 into u here, or 3 into x here, and 6 into x there, which would also work, but I prefer to keep everything in the original when possible. The classics, so to speak. Okay, so here's our integral cubed, and then the limits of integration will be 3 to 6. So we have 2/3 times, what do we got going on here? So plug in 6, we get -2, -2, no. Yeah, plug in 6, we get +2. +2 cubed is 8. Minus 3 minus 4 is -1. -1 cubed is 3. -1 cubed, -1. Seems reasonable, which gives us 9. 2/3 times 9, which equals 6. So our total area for here is 6. And so our total area from 1 to 6 will be 10. 4 plus 6. Okay, now we're going to go on to some more conceptual problems. This is more from previous Calc 1, but we should know this, so let's go for it. Won't take long, hopefully. For -5 is less than x, less than 6. On what open intervals? Open intervals means you use these brackets, not these brackets. And which means you don't have to include the endpoints, which just makes life simpler for this. If any, is the graph of f both increasing and concave up? Okay, so increasing means f prime of x is greater than 0, and concave up means f prime prime of x is greater than 0, which means that f prime of x is increasing. So we know that f prime of x, which this is a graph of here, is positive at 0 to 1. And, I don't know how I switched over to the eraser. I should learn what that function is. 0 to 1, it's going up, it's increasing and positive. From 1 to 3, it's not increasing, and from 3 to 4, it's also not increasing, so we know that the concavity is either 0 or concave down. But then from 4 to 6, we are again both positive on this graph and increasing. So 0 to 1, 4 and 6. Yes, yeah, that's true. Yep, I'm good with that. And give a reason for the answer, and that's because on these intervals, f prime of x is greater than 0, and f prime prime of x is greater than 0. So So this would be the justification right here. Find the x-coordinate of each point of inflection. So a point of inflection is where the concavity changes. Concave up to concave down. Yes, concave up to concave down. And the way concavity I look at intuitively is if it can hold water or not. Concave up means it can hold water. Concave down means it can't. So like here, this section from 3 to 6 is concave up because if you poured water, it would settle in there. But this is f prime of x, so don't go thinking that says too much about f of x. Okay, focus. Find the x-coordinate of each point of inflection. So we want to find points of inflection, we want to see where there's a change in f prime of x, or f double prime of x, which is g prime of x. So we want to find the x-coordinate of each point of inflection. Give a reason for your answer. So to do this, we want to look at f prime prime of x, which is g prime of x, which is basically looking at the slope of the current graph they show us right here. So here we go from decreasing to increasing. And when it goes from decreasing to increasing, you're going to have a change. This is going to be g prime of x less than 0 on this side, and on the other side you're going to have g prime of x greater than 0. And since you changed from negative to positive, in between there's going to be 0 at some point, and that's going to tell us that f prime prime of x over the same intervals is less than 0, f prime prime of x is greater than 0, so less than 0, greater than 0. Therefore, between the two, there is going to be a change in concavity. And therefore, at this point, because you have a change like that, you're going to have an inflection point. So for this, x equals 4, and the justification I would say would be something along the lines of g prime of x goes from less than 0 to greater than 0. And then I wouldn't say too much, that gets the idea across. And then you could be like, well, and then it goes from f prime, good enough. Okay, so this is the idea of finding area between curves. Next we'll start going over taking graphs, area between the curves, and then we'll revolve them around the x or y axis, and we'll find the volume of shapes rather than just area between curves. Thanks for watching. I will see you guys next time.